Hello everyone, my name is Axel and this is my first video in the mini-series about gravity. This video is going to be about gravitational field strength and weight, and I hope that you will enjoy. What will you learn today? You will learn the difference between mass and weight. You will learn what gravitational field strength is and its units. You will learn what is meant by apparent weight as opposed to real weight. And you will learn what is meant by weightlessness. So, you are all familiar with Newton's second law, F equals ma, which says that the force that an object experiences equals its mass times its acceleration. For an object on the surface of Earth, this equation can be written Fg equals mg, where Fg is the force due to gravity, m is the same mass, and g is the gravitational field strength given in meters per second squared. This Fg, force due to gravity, is what we also call weight. You might not be used to seeing weight expressed in newtons, because in everyday language we say that a person maybe has a weight of so and so many kilograms, but in scientific terms weight is actually a force. If we take a closer look at the terms in this equation, weight equals mg, we have the quantity m, which is the mass of the object. This quantity, mass, does not depend on which planet you're on, and it can vary from object to object. Objects can have different masses. We also have g, which is the gravitational field strength. And on the surface of Earth, it's about equal to 9.81 meters per second squared. And this is the gravitational acceleration on Earth's surface, and it is actually the same for all objects. The only reason that objects accelerate differently when we drop them here on Earth is because of air resistance. So if we were able to suck out all the air from a system and drop any object, it would accelerate at exactly the same speed as any other. And there is a famous experiment to show this, in which they are present in a vacuum chamber. They suck out all the air and then they drop a feather and a bowling ball together, and the results are fairly exciting.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1, release.
Exactly.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
We already know that the units of the gravitational field strength is the same as for acceleration, but it can be easily shown. If we just rearrange the equation weight equals mass times gravitational field strength, in favor of g we get weight divided by mass. If we now look at the units of g is newtons divided by kilograms. And if you recall, newtons is actually itself given by kilogram meters per second squared. So if we divide this by kilograms, we end up with meters per second squared, which is of course the same as for acceleration. The last term in this equation is of course weight, given in newtons, and this is the gravitational force that is acting on the object. This quantity in newtons is actually what your scale measures. It doesn't measure the mass in kilograms directly, but it measures the weight in newtons and then converts it back to give you a reading in kilograms. This is James. James is standing on a scale, and he has two forces acting on him. It's both his weight acting downwards, and it's the normal force that's exerted from the scale on James, and that keeps him from falling straight to the center of Earth. We know that since James is standing still, the two forces must exactly balance. Because if James was to accelerate, we know that they wouldn't be equal. Since he is not accelerating, the normal force from the scale is exactly equal to his weight. The normal force from the scale is what measures what is called the apparent weight of James. James's weight, the force acting downwards, cannot be measured directly, but the scale measures the counteracting normal force, which in this case is exactly equal to his weight. Then the scale uses the equation mass equals weight divided by gravitational field strength to give James back his actual mass. Now we've put James and the scale in an elevator. The elevator is standing still, so we know that the two forces exactly balance, just like in the previous case. And the apparent weight is therefore exactly equal to James's weight. But what happens when the elevator cable snaps and James and the scale are in free fall? Well, the normal force from the scale is no longer present, because the scale accelerates with James. The scale falls away from James at exactly the same rate as James is accelerating downwards himself. So there is actually an apparent weight of 0 newtons, because there is no normal force exerted on James from the scale. And that means that the scale will read to James 0 kilograms, even though James's real weight has not actually changed. That's the end of this video, and you should now know the difference between mass and weight. You should know what gravitational field strength is and its units. You should know what is meant by apparent weight versus real weight. And you should know what is meant by weightlessness. If you have any questions, please comment below and I'll respond to you, or you can save your question and ask me on Wednesday. See you next time!